of noise perturbed data distributions. How can we choose a stochastic process appropriately? We can use a stochastic differential equation whose general form is given here. It consists of two terms. One term is the deterministic drift term, which is what you would normally have in an ordinary differential equation. The other term is an infinitesimal white noise term with a scaling factor sigma t. And the solution of stochastic differential equations are stochastic processes due to this infinitesimal white noise term. Suppose we are already given a stochastic differential equation. How can we perturb the data distribution? Here is an animation. We essentially follow the stochastic process given by the SDE to gradually add noise to any data point. And this means we can perturb any image to noise. How can we find a stochastic differential equation for this purpose? We can use a very simple example here. There is no deterministic term. The only term is the sigma t times the infinitesimal Gaussian noise. If sigma t grows exponentially fast, then we can easily add more and more noise to convert any data point into pure noise. And after perturbing the data distribution, we hope to generate samples. If we can know how to reverse the perturbation process, then we will be able to generate samples. Suppose we have a prior distribution pi x, which is close to the data distribution perturbed with the largest noise. We can start from a sample from this prior distribution and reverse the stochastic process. This will gradually give us a sample without noise. And by following the reverse direction of the stochastic process, we can start from any noise to get a noise-free data sample. This procedure requires a stochastic differential equation to describe the reverse stochastic process. And luckily for any SDE, there exists a reverse time SDE. So for the SDE given on the left side, the reverse SDE is given on the right side. And the reverse SDE basically gives the same stochastic process of the solution, but with a reverse time direction. And here, the reverse SDE only requires the score function. And this score function is analogous to what we had before, the score of the noise perturbed data distribution, in this case, perturbed by a stochastic process. And now we can generalize everything to the continuous case with an infinite number of noise perturbations. So first, we have a time-dependent score-based model. Now it's conditioned on t, not sigma. The goal is to estimate the score function. Here, the training objective essentially generalizes the finite summation into an infinite summation, which is an expectation in this case. By minimizing this objective function, we can obtain the time-dependent score-based model. We can plug it into the reverse time SDE to get the following approximate reverse time SDE. And now we can use any numerical SDE solver to solve the reverse time SDE so that we can convert any random sample into we can convert any random noise to a high quality sample. And this procedure also unifies diffusion probabilistic models into the framework of score-based generative models as a special discretization to the SDE framework. And here is the result of this approach on the CIFAR-10 dataset. The CIFAR-10 dataset is a dataset of small images. It is a simple, but it is the most competitive dataset for generative modeling research. And on this dataset, we obtain very good sample quality as measured by FRD scores and inseparance scores. In particular, our method achieves 2.2 FRD score at 9.89 inseparance score. It's the state-of-the-art approach and then time better than the best GAN approach, which is the StarGAN2 with ADA. And even for StarGAN2 ADA with label information during training, we can still have better FRD score even without this label information. And the approach can be applied to high resolution images, for example, 1024 by 1024 images. Here, the model is trained on a dataset of human faces, and you can see you can synthesize high quality human faces as well. More samples of high resolution images. So a very important property of the SDE framework is that we can actually convert the SDE to an equivalent ordinary differential equation without changing the marginal distributions. And this ODE is called a probability flow ODE. given a SDE like this one, we can always convert it into an ordinary differential equation as given on the right-hand side of the equality. So the ordinary differential equation does not have a stochastic term, but it represents a trajectory with the same marginal distribution as the SDE. And here, the ODE only requires us to know the score function. The score function can be approximated by the score model. The samples from the probability flow ODE are in principle from the same distribution of the stochastic differential equation. And here is an illustration on what happens when you use ODE to do generative modeling. Here, the trajectories of ODE are given in white curves, and trajectories of SDEs are given in red curves. And essentially, we convert data to noise and convert noise to data. You can see that although the trajectories of the ODE and the SDEs are very different from each other, they actually share the same marginal distributions as given by the background of the curves. There are several advantages of the ODE framework. First of all, it allows more efficient samplers via the black box of these solvers. So here are some samples generated by the score-based models on human faces. NFE represents the number of score function evaluations. So you want smaller NFE for faster sampling. And in this case, when using ODE solver, we only require around 100 number of function evaluations for generating a high quality sample. When you use SDE solvers, you will probably need more than 1,000 number of function evaluations. So this amounts to a 10 times speed up. In addition to that, the ODE framework allows us to compute the exact likelihood, and the exact likelihood of our model, it corresponds to the data compression rate. So it's a very important quantity in generative modeling. In order to compute the likelihood, we only need to solve a one-dimensional integral, and this can be done with ODE solvers. And here are some results when using this ODE formulation. Again, on the CIFAR-10 dataset, you can see that we both achieve very high likelihood, which is 2.99 negative log likelihood, and very high FRD score, 2.92. This model is not even trained with maximum likelihood because it minimizes summation of score matching losses, but at the same time, it achieves the high sample quality and high likelihood. This is the first time that you can have a generative model to achieve both high sample quality and high likelihood. No other type of generative model are capable of the same thing. Sometimes you really want to have high likelihood. In this case, you can try to directly maximize a lower bound of the likelihood. And here is a theoretical result that connects the KL divergence, which is directly corresponding to the maximum likelihood training. It connects the KL divergence and the weighted combination of score matching losses used in our training. In the theorem, we show that the KL divergence from the data distribution to the model distribution is upper bounded by the mixture of score matching losses plus a KL term. Here, in the weighted combination of score matching loss term, the weighting function is given by sigma t squared, which we call the likelihood weighting. Remember, sigma t is a coefficient before the infinitesimal white noise term. The KL term is almost always 0 because P capital T is a noise perturbed data distribution, which is simple enough to be modeled by a prior distribution pi x. And this means the KL divergence is actually bounded by our loss function. And by minimizing our loss function, by also minimizing KL divergence, equivalently, we are also maximizing likelihood. And in addition, we can also compute the lower bound, the log likelihood, analogous to version autoencoders. And this computation does not require solving integrals, unlike computing the exact likelihood. It is also efficient for training those models. So this is what happens if we train our models to maximize likelihood directly. We can achieve 2.83 negative log likelihood on CIFAR-10 and 3.76 on ImageNet. Those results essentially challenges autoregressive models and version autoencoders on likelihood. Previously, those two model families are the best in terms of likelihood, but now we can essentially outperform them or obtain comparable performance in many cases. So finally, I will talk about some applications of this framework. The application is mostly associated with the controllable generation framework. So previously, we have talked about how to generate samples without any conditional information. And this procedure is described as first we have a data point x0, we apply a stochastic process to perturb x0 to get a noise vector x capital T, and we reverse this process for generating unconditional samples. If we want to condition the generation process, we will require a control signal y. And here, the initial data point x0 will be conditioned on the control signal y. And we apply the same stochastic process to perturb the conditional sample. And we reverse the whole process to generate a conditional sample given y from a noise vector x capital T. So this reverse process is captured by the following conditional reverse time SDE. And here we need to compute the score function of the conditional distribution. This term can be decomposed into two terms using the Bayes rule. And here, the new expression can be estimated first using the unconditional score function for the first term. The second term can be estimated by training a separate neural network, or in many cases, directly specified with our domain knowledge. And here are some applications of this framework. It can be used for class conditional generation with an unconditional score-based model. Here, the control signal y is the class label. The conditional distribution is the time-dependent classifier. And here are some samples generated by an unconditional score-based model, but with the help of the classifier, it can actually generate images belonging to a particular class. And the same method can be used for image impeding. Here, y actually represents the masked image, and the y given x cannot be specified with our domain knowledge. And with this formulation, we can actually complete the masked image in different ways to account for the stochasticity of the problem. And all the completions you can see to be quite reasonable. And the same method can be applied to colorization. Here, y is a grayscale image, and the generation can actually make the grayscale image colorful. And the approach can be applied to higher resolution images, like we can colorize the portrait of Lincoln to make it colorful. It can also be used for some innovative image editing tasks. Here, the control signal can be some stroke painting. And based on this conditional information, we can generate realistic images and satisfy the constraints of the original stroke painting. We can also use strokes to edit images. For example, we can use remove the water and some blue sky and another tower in those images. The samples look to be reasonable. Also, that's the appropriate editing according to our stroke painting. It can also be used for super resolution. Here, the control signal is a low resolution image, and given this control signal, we can generate a higher resolution image using a score-based model. And here, the second to last row shows the result from a GAN method. The last row shows the result from score-based model. Those are results given by researchers from the University of Texas and Austin. So you can see that compared to the GAN result, our results do not have the white Obama issue, and the score-based generation models are in general can produce samples that are fair in terms of the minority population in the training dataset. And in addition to this, the controllable generation approach can be used to solve many inverse problems in science and engineering. For example, for medical imaging. In medical imaging, we hope to generate medical images from various measurements of the human body. For example, in MRI, we use magnetic field to measure the human organs, and in CT, we use X-ray projection to measure human bodies. In those cases, the control signal are actually given by the medical imaging machines, and we hope to generate samples conditioned on the measurements. And here, the y given x probability distribution can again be specified by the physical measurement processes. And we apply a score-based model to medical imaging as well. And this is the result of our approach, and this is the ground truth. You can see our approach is the best compared to alternative methods. And even more, our methods are the first unsupervised or generative method that can work for both sparse view CT and accelerated MRI, and also some artifact removal as well. Those methods can actually outperform supervised deep learning methods that are specifically trained for those tasks. And finally, from language to image generation, given some prompt, you can also generate the corresponding images.